Hey everybody, today we're going to be talking about Graham's law and Maxwell-Boltzmann distributions. And when you look at that, you're like, oh my gosh, that's kind of a mouthful there. But really what we're going to be talking about are gases and their speed. And so if you keep in mind that it's really just talking about how fast gases are moving, all of this seems a little bit less stressful. So I guess buckle up for this, but it shouldn't be too complicated. When we get started, there's a couple things I just want to review with you that we already know about gases. So gases we know are zipping around very quickly with very little intermolecular attraction between gas particles. So there's not a lot of sticking together that happens between gas samples, especially if they are at low pressures and high temperatures, because they're moving around fast enough that they can kind of hit each other on the sides of their container. So they move around in those lines until they hit things. And we also know, just from experience, that gases that are warmer have a higher average kinetic energy than those that are colder. So if you think about that on a physical sense, the particles, when they're hotter, are moving faster than particles that are colder. And you should have seen that in your simulation. So we kind of know that already. But what we haven't talked about is what equation we use to calculate this kinetic energy that we speak of. And there is a relationship between kinetic energy and temperature that the AP exam isn't going to ask us to investigate, but there is an equation, and if you are interested in that, we can talk about that at another point in time. What we're going to be talking about is just this kinetic energy equation here. So this equation is given to you on your equation sheet so that it's there as kind of a reference. I don't know if I have actually ever seen them use this in a calculation. It's more there to kind of help you go through the thought process of explaining something. So in this equation, KE is kinetic energy and it's measured in joules. And the kinetic energy of your gas is equal to 1/2 times M. And M is the mass of your particle. Now, in this case, we typically would use like the molar mass, and that would be in kilograms, or it could be the actual physical mass of your sample. And then V here is the velocity, which is just a fancy name for speed. And that is in meters per second. So if you think about this, your kinetic energy has two things that tied together. It's how heavy your particles are and how fast they are moving. So if they are moving faster, they are going to have a higher kinetic energy, which is what happens at a higher temperature. Also, if you have two particles that are like heavier than each other, the one that's heavier is going to have a higher kinetic energy if they're moving at the same speed. It's kind of like if you have a car accident and you hit a tree with a semi versus a smart car, there's going to be a different amount of kinetic energy and like a violence level to that crash. Wow, I took that to a really dark place. Sorry about that. But anyways, this is the equation. We're going to talk about gas particles and not tragic car accidents. So just sorry. Okay, so let me go back for a second. When we talk about the speed of our particles, the problem is with gases that we say that if they are at the same temperature for all the particles in a gas sample, they have the same average kinetic energy. But what that really means is that some have higher kinetic energy and some have lower. But if we put all of their kinetic energies together and divide them by how many particles are, they'd have the same rough average kinetic energy if I looked at one sample of gas versus a different sample of gas. So the speeds of individual gas particles actually vary quite a bit. And what they can do to kind of show us where your varieties of speeds are for your different particles is through something called a Maxwell-Boltzmann distribution. So this is one of those distributions, and you can see here on your y-axis, it's the number of particles, and on your x-axis, once my little thing goes away here, it's the speed of your particles. So what it's basically showing you is at any point, if you have a particle that's at a given speed or velocity, how many particles are there? Now, it's not the actual like quantities in here are not important. It's the rough shape. that's there. So at the very peak of your Maxwell-Boltzmann distribution is the most probable speed. So the largest number of particles are going to have this speed. Your average speed, though, is generally a little bit higher than your most probable speed, because if you think about this as a curve here, we have particles that have some that are very, very slow and some that are very, 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 very fast. And so if you think about the total number of particles, it kind of shifts our average a little bit more away from the probable speed or the most probable speed, and our average speed is just a little bit higher than that because of all the different particles that are kind of up here. So we talk about a Maxwell-Boltzmann distribution. You're very rarely going to be dealing with something that's just looking at one gas and identifying a particle. What they're going to do is they're going to ask you to compare distributions of either two things: one, different temperatured particles, or two, different types of particles. So we're going to talk about different temperatures first, and then we'll get into different types of particles. So here is generally how your distribution curve changes when we change temperature. If you think about green as the previous curve that we saw there, your room temperature gas has its shape. If I have a cold gas, what happens is my peak for my most probable speed shifts to a lower speed, because at a lower speed, they have less kinetic energy, okay? So I have less speed, I have lower kinetic energy. So on average, my particles are moving slower, so my peak shifts more to the left, as you can kind of see here. The other thing you're going to notice is that that peak shifts up as well. And it shifts up because more particles are going to have that most probable speed, because if you look, my distribution of possible speeds is much smaller. So if you notice, the actual physical width of the curve, or the possible speeds that are there, is a much more narrow range than it is for a room temperature gas. So what you have is a colder gas where more particles are going the same speed, but there are less total different speeds for your gases. And kind of the opposite is true if we're talking about a gas that's warm. And you can see here on the curve, if I take a gas and I heat it up, now the particles are going faster. So what it does is it stretches out my highest possible speed that I am going to have for my gases. And when that happens, it drops the number of molecules at that given speed, because there's just more possible speeds for it to have. And it also shifts our probable speed and our average speed higher because they have a higher kinetic energy. So hopefully that makes sense to you. Cold gases move slower, but there are more particles at a given speed. Hotter gases than your room temperature gases will have a higher speed, but they will have less gases, or less gas particles at that specific speed, okay? So that is gases at a different temperature. Now, gases that are at the same temperature but are different types of gases have the same kinetic energy regardless of what it is. So if we're talking about, let's say, carbon dioxide versus carbon monoxide. If I have two gases, if they are at the same temperature, they have the same average kinetic energy. And that is really important. Now, like I said, I don't think you're going to have to do a calculation with this, but conceptually, you're going to have to understand it. So if we are talking about, let's say gas 1 is carbon dioxide. Carbon dioxide weighs about 44 grams. If I have gas 2 being carbon monoxide, let's do the math quick, it's about 28 grams. So 44 grams versus 28 grams, I'm going to have a difference in terms of how fast those particles are going, because they both equal out at the same kinetic energy value. So if you think about it, if I have carbon dioxide here and it is equal to whatever that kinetic energy is for that temperature, if carbon monoxide has a mass that's lower, but this number in the middle needs to be the same, that means that my speed has to be higher for those particles. So they have the same amount of energy, but because they weigh less, they can move faster, okay? So think about it that particles that are lighter move faster, than heavy particles at the same temperature. And that's generally the idea behind this. So what I have here is actually a plot of your noble gases at 31 Kelvin. And I picked 31 Kelvin because it helped me get helium on the curve. But what you'll notice is in terms of our speed here, it's the same type of shape that we see with our different temperatures. Now we just have different gases. So my fastest, most likely speed or most probable speed is coming from helium, and helium is the smallest of our noble gases. My highest number of particles, but also my lowest speed comes from radon, which is our heaviest noble gas. So the idea is that if I have this kind of big tank of a gas of radon, which weighs 222 grams per mole, so that's it's over 100 times. Nope, I can't do math, sorry. But it is heavier than helium by a lot. Helium is 4. So, over 25 times heavier. So in that situation, I am going to have this big tank of a particle for radon that's moving around slowly compared to helium, which can kind of zip around and move around really easily because it is significantly lighter. And so that's kind of what happens with these. So your distribution curves are different, whether it's temperature or weight, but it means the same thing. If something's moving slower, it's got a higher peak and it has a narrower range of values for its speed. And if something is moving faster, it's got a wider range, but a lower peak is generally how it works. Now, this is important, and the types of questions that I think I would expect on the AP exam. You could be asked to draw a graph or draw how a graph changes. So that's totally within the possibility of what you could see. But I think what will likely happen is you will get a question either conceptually or you might have to explain it, or you might have to just do a multiple choice question on either diffusion or effusion. So what diffusion is it's when a gas disperses in a container, and it could just be one gas or it could be two gases. It just kind of depends. And what ends up happening is that if I have two separated gases and then I open the container between them, so if you think about this is two bulbs of gas, and then I open what they call the stopcock. It's the same thing that's in a burette. It's just a little valve, basically. If I open that and I have two containers, one in this case with hydrogen and one with oxygen, hydrogen weighs 2 grams per mole-ish. Oxygen is 32 grams per mole. So because the oxygen is a heavier gas, it's going to move slower, and it will not mix as fast as the helium mixes. The helium is going to mix faster. If you give it enough time, they will mix evenly and reach an equilibrium with the particle distribution. But initially, there's going to be a big rush of helium from the helium side because they can move a lot faster. So think about this is a particle container of hydrogen, not helium. So hydrogens are scooting around really fast and they're moving faster. So when they go into the oxygen side, they just can get in there faster because they are literally moving faster. Okay. The other circumstance that they could ask you a question about is effusion. And now I feel like it's a much less obvious situation, but the argument is still the same. So what effusion is you have essentially a two-chambered container, and there is a separation between them, so like a physical barrier. And then in that physical barrier, there are tiny holes. And then on one side of it, there is a vacuum or a lower pressure situation. And what will happen is the same thing. If I have two gases and one is heavier, but they're at the same temperature, the gas that's heavier is going to move slower and will move through the hole less frequently than something that's lighter. Now you say to yourself, what in the world is a practical application of this? And it's actually kind of interesting. So when they make nuclear weapons or nuclear fuel rods for plants, they more often than not like to use uranium-235. So uranium-235 is better for fission and all that kind of stuff. And so when they enrich uranium, what they want to do is they want to basically amp up the amount of uranium-235 and then not so much with the 238. So if you think about it, in most samples of uranium, there's some uranium that weighs 235 and some that weighs 238. So what they can actually do is set up an effusion chamber, and then you will get the 235 moving into the low pressure side or the vacuum side of it. And then you'll get more 235 coming out. And then that's how you enrich your uranium, because you get the 235 more than the 238. And so they call that enriched uranium if it's higher percentage 235, and it's depleted if you take the 235 out and then you don't have a lot of that in there. Okay, so just some kind of practical examples of this. Like I said, on the test, they're going to ask you questions, I think, more conceptually. So if you understand cold gases move slower, and you understand that heavy gases move slower at the same temperature, then I think you're going to be okay. All right. So give your homework a try. If you have any questions, please let me know and we'll get things cleared up. Good luck.